suppose we have a dephasing channel. And let's say that's 1 minus q. You apply a sigma z, and the probability q. 1 minus q, you apply nothing. Probability q, you apply to sigma z. Probability of error is, well, you get an error if you apply a sigma z to any qubit. So, and you don't get an error if you apply sigma-z to an even number of qubits. So it's 3q plus q cubed. 3q, 1 minus q plus q cubed. 3q, 1 minus q squared plus q cubed. Around 3 times the chance of error, of unencoded error. Sigma z, I want to say this is 3 times the chance of sigma z error on an unencoded qubit. But if you have a d-bitting channel, if you have a channel 1 minus q sigma x, 1 minus q identity, and q sigma x. Probability of error, well, you need at least 2 of these qubits to be wrong, to have an error in the original an encoded qubit. So the probability of the error is q 3q squared 1 minus q plus q cubed. So this is quadratically small if q is small, and this is 3 times 3q if q is small. So we've corrected the bit errors, and we've made the phase errors even worse. Okay. Now, you probably know that Hadamards interchange phase errors and bit errors. So intuitively, this should mean that you can take this code and Hadamard it and get a code that corrects bit phase errors but makes bit errors 3 times as worse. So let's do it. The bit code, or the bit correcting code, was 0 goes to 0, 0, 0. 1 goes to 1, 1, 1. So let's take H. So let's say this is the phase code. It's going to take H0 to H cubed 0, 0, 0. H1 to H cubed 1, 1, 1. And this is just 0 plus 1, 1 over root 2, goes to 1 over root 8, 0, 0, 0 plus 0, 0, 1 plus dot, dot, dot plus 1, 1, 1. And 1 over root 2, 0, minus 1 goes to 1 over root 8, 0, 0, 0, minus 0, 0, 1, through minus 1, 1, 1. And this is minus 1, the number of ones in the state. So we worked this out for Simon's algorithm. And this is what Hadamard cubed does. It takes puts a minus 1 on any state with an odd number of ones. We can add these and we can subtract these to get what our code does to 0 and 1. So phase code, 0 goes to 0, 0, 0 plus 0, 1, 1 plus 1, 0, 1 plus 1, 1, 0. 1 goes to 1/2, 0, 0, 0. Oh, sorry. 0, 0, 1 plus 0, 1, 0 plus 1, 0, 0 minus 1, 1 plus 1, 1, 1. So you take 0 to the superposition of states with an even number of ones, and 1 to a superposition of states with an odd number of ones. Because when you subtract this from this, you only get states with an odd number of ones, and when you add these, you only get states with an even number of ones. So you can correct this, and actually it should be obvious that you can correct this because all we did was we put a Hadamard in front of everything. So just take your old correction circuit and add a whole bunch of Hadamards, and you get the new correction circuit for the phase code. But I want to explain it a different way. So let's call this a logical 0, and this a logical 1. So logical 0, logical 1, sigma z on the first qubit, logical 0, sigma z on the first qubit, logical 1, sigma z on the second qubit, logical 0, etc., are all orthogonal. Well, we can see that up here. I mean, we can, first clearly 0 and 1 are orthogonal because none of these basis states in the superposition of 1 appears in the superposition of 0. And when you apply a sigma z to any of the bits, this is still true. So any sigma z error on 1 is orthogonal to any other sigma z error on 0. And further, if you apply sigma z error to 0, so sigma z on the first qubit of 0, logical 0, is equal to 1 over 2, 0, 0, 0, plus 0, 1, 1, minus 1, 0, 1, minus 1, 1, 0. So half the terms here are plus, half the terms here are minus, so this is orthogonal to that. And it's easy to check that all of these are orthogonal. So project onto subspaces 0, L, 1, L, 0, sigma z1, 0L, sigma z1, 1L, etc. So these are 4 orthogonal subspaces. So this is a measurement that projects a state onto one of these 4 subspaces. And in this case, if you get this subspace, you do nothing. If you get this subspace, you apply sigma z to the first qubit. If you get the next subspace, you apply sigma z to the second qubit, etc. So this shows you how to correct these errors.